Suppose we wish to find the line tangent to the curve described by the equation e to the y sine x minus 1 equals x plus xy minus pi over 2 at the point pi over 2, 0. So we have here an equation giving us an implicit description of a curve. There's a certain set of xy pairs that satisfy this equation, and we could plot those points. But looking at where y and x are located, y is both inside of an exponential function and also part of a polynomial. X is part of a polynomial and also inside a sine function. We're mixing polynomials with transcendental functions. More often than not, this means that we cannot solve for one variable in terms of the other explicitly as a function. So we just sort of have to deal with this as it is. We're given a particular point at which to find the tangent line. This should be a point on the curve. It's a good idea to make sure that we are reading and understanding the question correctly by plugging this point in and making sure that it works. So putting in this xy pair, x equals pi over 2, y equals 0, just as a quick little check there, we have e to the y, well, e to the 0 is 1. We have the sine of pi over 2, that's 1. So we have 1 times 1 minus 1 on the left-hand side. On the right, we have x is pi over 2. X times y, well, y is 0, so that is 0, and minus pi over 2. And we see we have 0 on the left, 0 on the right, so that checks out. This point is on this curve, along with infinitely many others, but at least we know that that is going to work out fine. So we want to find the tangent line to that. We have the point, we just need the slope, and of course the slope comes from the derivative. Since we cannot solve for one variable in terms of the other explicitly, we need to differentiate implicitly. And I will work through a couple of different notations of this. First, I'll go through the problem carefully using very careful and precise and thorough notation. It is very clear, but it may be somewhat cumbersome. And then after this, I'll show a couple of ways, a couple of things we could do to speed up our computation here. But first, let's just be very careful and step by step about things. So the idea is that we have an equation, and we can do pretty much anything we want to an equation as long as we do the same operation to both sides, and it's a consistent operation, a deterministic thing. So, a classic example is, say you want to get rid of this minus 1 over here, you could add 1 to both sides of the equation, because adding 1 is an operation that if you start with the same value, if you add 1 to it, you'll always get the same value. So if we start with two things that are equal, and we add 1 to both of them, the results will be equal. Okay. Now, an example of an operation you could do with expressions like this is to take a derivative. If we start with two expressions that are equal, and we differentiate each of them with respect to x, so we'll take d by dx of the left-hand side. So if we differentiate the left-hand side, and also differentiate the right-hand side, if the original two expressions were equal, then their derivatives should be equal. For any particular, x, y location we have on this curve. Okay. Now this doesn't necessarily go back. Antiderivatives are a more complicated thing we'll talk about later. But that's okay. Not all operations we would do to both sides of an equation are reversible anyway. All right, sometimes you will square both sides of an equation, but that is not strictly reversible. So this is fine. So now we just need to differentiate both of these sides, both sides of this with respect to x. Let's just go on through and we'll find the derivative of y with respect to x, because that will give us the slope as a change in y over change in x. And then we'll worry about the point at the end. So let's, again, like I said, take this very carefully, step by step. We have a derivative of a difference here. and this is a product. So we can write that as the derivative of the first factor, e to the y, times the second factor, sine x, plus the first factor, e to the y, times the derivative of the second factor. So we have d by dx of sine x minus the derivative of 1. And that is equal to, on the right-hand side, we have the derivative of x plus, now we have another product here, so we'll use the product rule again. We have d by dx of x times y plus x times d by dx of y. So again, we're differentiating the first factor and the second factor. And finally, we have minus the derivative of pi over 2. So one thing to be careful of when differentiating implicitly is to think about all of the things that are variable, right? You've seen past examples where sometimes certain quote-unquote variables are treated as constant because they are not what we're differentiating with respect to, right? You could have a parameter like an a or k or n that's floating around in there, and that just means some constant, and we treat it like a constant. But here, we're differentiating with respect to x, but we're thinking of y as depending on x, so y is also variable, right? Y is a sort of a function of x locally. So we have to handle all of these as variable expressions. So let's start evaluating this. We have the derivative with respect to x of e to the y. Well, the derivative of an exponential function is itself, so we have e to the y, but y is not x, and that means that the chain rule tells us that we have to multiply that by the derivative of y. That is dy by dx, the derivative of y with respect to x. So this is just handling this derivative right here, and we've got this little chain rule part that might be a little tricky. So I'll talk about that more in a moment. Now we're adding e to the y times, we have d by dx of sine x. This is a little bit more straightforward. The derivative of sine is cosine, so we have a cosine x there. Minus the derivative of 1. Well, the derivative of 1 is just 0, so let's not bother writing that here. We have the derivative with respect to x of x. The derivative of x is just 1. If you think about that, you could even see that, a lone variable we can just kind of put into the numerator there, and you have dx by dx. Well, that ratio, that differential divided by itself should be 1. Plus, and again we have the derivative of x, that's just 1. 1 times y is y. Plus x times the derivative of y, that is dy by dx, minus the derivative of pi over 2. Pi over 2 is constant. Again, this is 0, so we can leave that off there. So now we have e to the y times the derivative of y times the sine of x plus e to the y times the cosine of x equals 1 plus y plus x times the derivative of y. Now, I want to mention something very important about the notation here that you want to be careful of. With Leibniz notation, when you have something like this, dy divided by dx, that we think of that as a ratio of differentials. dy is a differential, dx is a differential, and this represents a quantity, and that quantity is the derivative, okay? When you have something like d over dx, this is what we call a differential operator. D over dx is not a quantity, it's not a derivative, it's a symbol that means we want to take the derivative with respect to x of whatever the next thing is, okay? So this d by dx is saying we need to take a derivative of something that's following. So this d by dx of e to the y, that's like a function. E to the y, we're taking the derivative of that, and it becomes e to the y times dy by dx. Okay. So this is a kind of a function application. It's not a multiplication. Here, though, dy by dx is itself a derivative. This is a quantity with numerical value at a particular point. So this is not telling us that there are any derivatives remaining to take. This is a function that's being multiplied by these other two functions. Okay. I know the symbols look a little bit similar. Practice with them and pay close attention to kind of separate them in your head. They're related, but one is an operation that's telling us we are taking a derivative of the thing that follows, and this other one is itself already the derivative. Okay. We have this equation, and this is an equation that is implicitly relating x, y, and the derivative of y. We would like to find what the derivative of y is, and to do that, we want to get it by itself on one side of the equation. And in order to do that, we first have to get all of the terms that have the derivative of y on one side of the equation. So let's pull everything together and I'll rewrite, well, no, let's do that how it is, that's fine. So we have e to the y times dy by dx sine x. You could rearrange this if you want it in a different order, it doesn't really matter. And looking throughout here, we see that over on the right-hand side is also a term that contains the derivative that we want. So let's subtract that from both sides. So that gives us minus x times dy by dx. Okay, so we're subtracting this term from both sides. That allows us to kind of shuffle this derivative term over to the left. Now all of our derivatives are on the left-hand side. There's also this term here, this e to the y times cosine x. That doesn't have a derivative in it. This is just in the way. So let's move it over to the right by subtracting it from both sides. So now we have 1 plus y minus e to the y cosine x. So this step was just algebra. I was subtracting e to the y cosine x from both sides and also subtracting x times dy by dx from both sides, just to kind of rearrange the terms of it. So this is progress. We're trying to get dy by dx by itself. Every term on the left has that in it, but it's showing up twice. So there isn't a single step we can take right now to easily and obviously isolate that. But since it is in both of the terms on the left, let's factor it out. We can write dy by dx times e to the y sine x minus x. Just factoring that out of both terms there. And that is still equal to 1 plus y minus e to the y cosine x. Now you see, hopefully we can finish this off easily. We can get, I'll put it over here so that the equal signs are at least close to lining up. dy by dx is equal to, we have this quantity here that we can just divide off of both sides. 1 plus y minus e to the y cosine x divided by e to the y sine x minus x. Now, of course, we want to, this only works if this quantity is non-zero. So depending on what we're doing with this, we might have to be more careful of it. But in general, this is what we would expect for the derivative. So if this were all we were asked for in this problem, find the derivative, that would be the answer, right? We'd look to see if we can simplify anything further. There aren't really like common factors we can take out of that or anything, so that's about as simple as that gets. So if that's all we were looking for is the derivative of y with respect to x, there we would be. However, that's not what we were asked to do in this problem. We were asked to find the tangent line at a particular point. At the point pi over 2, 0, dy by dx is equal to, well, let's plug this stuff in. We have 1 plus y, which is 0, minus e to the 0 is 1, but the cosine, well, I'll go ahead and put this in. e to the 0 is 1. We have the cosine of pi over 2, but that's 0. This is divided by, again, e to the 0 is 1. We have the sine of pi over 2 is 1, minus x there, which is pi over 2. So those terms are 0 in the numerator. We have 1 divided by 1 minus pi over 2. Compound fractions aren't great. Let's clear out the 2's. We'll multiply by 2 over 2, and we have 2 divided by 2 minus pi. So at this particular point, pi over 2, 0, the derivative, dy by dx, is equal to 2 over 2 minus pi. That means that this is the slope of the tangent line at that point. So now we just need to write that, put that into an equation form. A couple ways to write a linear equation. In this case, let's use the point slope formula. So we have y minus our fixed y point, that's 0 here, equals the slope, 2 over 2 minus pi, times x minus the known x value. That is pi over 2. So y minus 0 is just y. We have, how do I want to write that? Let's leave that out front. We could put the x into the numerator and make that 2x over 2 minus pi. But let's go ahead and write it like this to make it a little bit clearer at a glance that that is just a constant times x. And then we have minus 2 over 2 minus pi times pi over 2. We see the 2's cancel, and that simplifies to pi over 2 minus pi. And that should be it. And indeed, if you use a piece of software that is sophisticated enough to graph an implicit curve, and you have it graph this original equation here, and also graph this line at the same time, so you have both of those graphs, you will see, I did confirm this earlier, you will see that this line is tangent to the curve at the given point. So, this was a little lengthy. I wanted to, like I said, I wanted to very carefully show some of the notation and be very careful to illustrate how we are, how implicit differentiation works, what we're doing. We're just taking derivatives. All the same rules still apply. It's just we have to be a little bit more mindful because now we're taking derivatives of y, expressions that involve y, which is a function of x. So, but the same stuff involving product rule, chain rule, if you have a quotient, use the quotient rule, whatever, all of the standard derivative rules just apply as normal. And this is, as I said, this is a very precise way of writing it with all of these differential operators and these derivatives that we have here. But it can be somewhat cumbersome. So let's come back to this again and think about the derivatives. But this time, instead of using the dy by dx notation, let's use the prime notation to make it a little bit more compact. So if we're taking the derivative of the left-hand side, again, we have the product. There's no way around that. So first we'll take the derivative of e to the y. That'll be e to the y times the derivative of y. So we have y prime. Always be careful with your primes to make sure that it's a very clear mark, not easily overlooked, and that it doesn't look like a first power or something. Sine x plus e to the y times the derivative of sine x, which is cosine x. And this equals, on the right, taking the derivative with respect to x, derivative of x is 1. We have this xy, so again we'll use the product rule. Derivative of x is 1, so we have 1 times y, plus x times the derivative of y, and the derivative of y is y prime. Derivative of pi over 2 is 0, so we have this. This is a lot less writing, but it's also less clear, so be very careful with it. I would recommend at first use the Leibniz notation. Do that at least once. Make sure you understand what's happening there, working very carefully step by step. And if you understand what's going on and you feel comfortable with it and you want to use the prime notation after that, that's fine. Feel free. But you may find that the primes can be somewhat confusing in certain situations. If you're not too certain about your dependent and independent variables, then you might want to avoid that. But anyhow, so from here, we have this this whole setup. This is that expression. If we wanted to continue to find the derivative, we could solve for y prime just like we did before, right? We take every term that has a y prime, put it on one side. Every term that does not have a y prime, put it on the other. Factor out, divide, and you get the exact same expression. However, this particular problem lends itself to a shortcut, because it does not ask us for the derivative. If it did, we would have to do that. We would have to do just what I said. Solve for y prime, get y prime equals, and you'll have exactly the same expression we had before. But it doesn't actually ask us to find the derivative. It just asks us to find the line tangent to this curve at the point pi over 2, 0. Now, we need to know what the derivative is at that point in order to find the slope of the line. But we don't need to know what the derivative is at all of the other points. So now that we have differentiated both sides, and we have an expression relating the derivative to x and y, if all we care about is the derivative at this one point, we can now just go ahead and substitute in for that one point, right? E to the 0, y prime sine pi over 2, plus e to the 0 cosine pi over 2 equals 1 plus y, which is 0, plus x there is pi over 2, y prime. Right, just plugging in the things that we know. E to the 0 is 1, sine of pi over 2 is 1, so we have 1 times y prime times 1. We have, let's see here, e to the 0 is 1, cosine of pi over 2, though, is just 0, so that's gone. We have 1 plus 0 plus pi over 2 y prime, and now we have a much simpler equation to solve, right? We have y prime minus pi over 2 y prime equals 1. Can factor out the y prime, have y prime times 1 minus pi over 2. Oop, that got sloppy. Sorry. Let's try that again. Pi over 2, which equals 1. And now, dividing both sides, we have 1 divided by 1 minus pi over 2. And again, we'll clear out that fraction there and get our 2 over 2 minus pi. And then we just stick that in and finish the rest to find the line like we did before. That is a lot less work, and there are two reasons. One of them is just getting to this stage. I skipped a lot of steps. I didn't write out all of the individual steps, and I used a much more compact notation. So that was part of it. But even once we have this, you see that if we only care about the derivative at a single point, after we have finished differentiating, we can just plug in the values for that point, and we get y prime at that one point, because this is the only derivative we care about. That's the only tangent line slope we want in this problem. Again, that's only because we're only asked about a single point. If we might have wanted more, we should probably find the derivative in general. But in this case, we can narrow it down to just that. Do be careful not to substitute in your point too early. You have to make sure that you have finished taking derivatives, because once you substitute in the point, you are now looking at just that one point, and if you try to take any further derivatives of that, that point is just constant. It's not moving, there's no curve. The derivative will just be 0, right? So if you begin by plugging in pi over 2 for x and 0 for y, if you plug that into this equation, you just get 0 equals 0, and that's not useful, right? Even if you don't simplify all the way and you leave them constants, as soon as you take the derivative, you just get 0 equals 0. So you do have to make sure not to plug in too early. So, when in doubt, maybe hold off a little bit if you're not sure if you can plug in your point yet. But that is an option. Once we don't have any more derivatives to take, we can, if we only care about a single point, we can plug that in and solve a little bit more efficiently.